Hi everyone, my name is Kyle. I'm going to be doing an integral that I ran across not too long ago. It was quite a long integral to do. There was a few substitutions that needed to be made, but eventually I got it. So I'm going to show you how to do this integral if you ever have to do it. So hopefully you don't have to, but if you do have to, you'll know how to approach it. So it's the integral of 2r dr over the square root of r squared minus big R squared times 1 plus r squared over b squared to the minus 5/2 power. That was a mouthful to say, so let's just simplify it a bit. I'm going to rewrite the integral in a slightly less intimidating way, so I'll just have r squared minus r squared to the half. Then I'll have 1 plus r squared over b squared to the positive 5/2. I'm going to factor out of this expression, I'm going to factor out a 1 over b squared. And you're going to see why I'm doing this. 1 over b squared, that just factors out of b squared plus r squared. Now this is still to the 5/2 power. And then if you distribute this 5/2 to each term, this ends up being 1 over b to the 5 b squared plus r squared to the 5/2 power. So notice this 1 over b to the 5 on the outside. It's in the denominator in this expression. It's a fraction, and it's in the denominator, which means it can come up to the numerator, so just multiplying by the reciprocal. So this ends up being r to infinity. Now we have 2r b to the 5, it's just a constant. Then we have over r squared minus r squared to the 1/2 power. Then we'll have r squared plus b squared to the 5/2 power. So slightly less intimidating integral, but still not entirely trivial. So what we're going to do now is I'm going to make a u substitution. We'll just say u is equal to r squared plus b squared. Okay? So we have that, and now we're going to have du is equal to 2r dr, and I totally forgot the integral sign up, the dr up here. So that's good, because I have a 2r dr in my numerator, so my differential of u can replace the 2r dr in the numerator, and the b to the 5 is just a constant, so that could just come out of the integral sign. So if I have u is equal to r squared plus b squared, then we'll have the integral of b to the 5. Integration bounds are going to come later, but 2r dr right here, so this 2r and this dr is just my new du. So just going backwards here, we'll just have du in the numerator. And then, okay, so let's try and rewrite this. So r squared minus big R squared, using the fact that u is equal to r squared plus b squared. So if you have u minus b squared, that's equal to r squared, just from this definition right here. And then you can do u minus b squared minus big R squared is equal to r squared minus big R squared. Right? So the term in the denominator right there, that will end up becoming u minus b squared minus r squared to the 1/2 power. And then we're going to have r squared plus b squared, that's just u, that's u to the 5/2 power. And what we're going to do now is look at the integration bounds. So the integration bounds is, so we have the substitution u is equal to r squared plus b squared. If little r is equal to big R, that means, so if little r is equal to big R, u is equal to big R squared plus b squared. And then if r is equal to infinity, then u is equal to infinity, right? So that shouldn't be too bad to see. So we'll have from r squared plus b squared to infinity, infinity in the integral. Okay, so we're making some progress. Still not a very nice form here. So we're going to need to use another substitution, right? So notice we have this u minus b squared minus r squared term. So what I'm going to do now is I am going to say, let's see, what's the best substitution to do right here? If you have something of the form like x squared minus a squared, right, you usually have a substitution where you say let x equal to, I think it's a secant of theta, right? In this case, I don't have an x squared, but that's okay. What I can do is say, let's just say, let u to the 1/2 is equal to the square root. So let's just make sure I'm doing this correctly, because I'd hate to mess up at this point. So I have u minus b squared minus r squared. That's just equal to u minus quantity b squared plus r squared, right? So that means we can make a substitution. Let's say let square root of u equal square root b squared plus r squared secant theta. I know that's hard to see. Ooh, you can't see it on the screen, so sorry, I went a bit too far. So let me just drag this back over. Okay, that was not a good drag. This should be a good drag here. Okay, that should look better, right? So that's what I'm saying now. That we're going to make the new substitution that the square root of u is equal to b squared plus big R squared times the secant of theta. Wow, right? So another substitution on our way. So let's just make sure we don't miss anything here. So let me just double check. Okay. Okay, so we're going to say u to the 1/2 is equal to square root b squared plus r squared times secant of theta. So then we take a derivative of this, so we'll have 1/2 u to the minus 1/2 du is equal to, keep the constant out front, b squared plus r squared. Now the derivative of secant is secant theta tangent of theta. All right. And then I want to do some more manipulation here. Du should equal 2 times square root b squared plus r squared secant theta tangent of theta, and then this is all divided by u to the minus 1/2. Right, just making sure I'm not losing my mind here. So I have u to the minus 1/2 in the denominator. That just ends up becoming u to the positive 1/2 in the numerator. So u to the 1/2 up here, but u to the 1/2 is already something I see, right? So u to the 1/2 is given up here. So substituting, I'll get 2 times 2 factors of b squared plus r squared to the 1/2 just gives me a factor of 1. And then I have a secant squared theta times a tangent of theta. So that's my du. Yes, another substitution. Wow. So let's now go ahead and plug everything back in, but now we have to remember we have new integration bounds. So let's work on the integration bounds now. So the integration bounds of this integral, we went from, well, first off, we had u to the 1/2 is equal to square root b squared plus r squared secant of theta, right? Which means, okay, so let's say, then we have u, right? So u is just the square of both sides. So we have b squared plus r squared times secant squared of theta. Okay, so I want to make sure I'm doing everything right here. It's like a lot of back and forth, I know, but with all these, you know, u's and b's and r's, you just want to be sure you're doing everything you can to be consistent. So I think I'm good. So okay, so let's do this now. So u is equal to this, right? And now if the lower bound is r squared plus b squared, so if u is equal to r squared plus b squared, remember this is still multiplying that. Then we have r squared plus b squared is equal to it's equal to r squared plus b squared secant squared. Then I cancel these on both sides, so you have 1 is equal to secant squared of theta. And actually, I didn't do this last time. This is interesting. This is very interesting. But we have 1 is equal to 1 over cosine squared of theta, right? Okay. So where is cosine of theta equal to 1? That's at 0. So theta is equal to 0, right? And then on the upper bound we have infinity. So we have if u is equal to infinity, we have infinity is equal to 1 over cosine squared of theta. So when does this blow up? Well, where is this 0, right? So where is that 0? That's at theta is equal to pi over 2, right? So if you have where the denominator is equal to 0, right? So if 1 over 0 is infinity, then we have theta is equal to pi over 2. So our new integral, yet our third rewriting of this integral, is going to have, we got to make sure we have everything right? So we have to look at the top. We have, okay, so we have b to the 5 outside. We're going to have the integral going from 0 to pi divided by 2. Now du, right, we have du in the numerator. Du is just 2. I think I'm just going to copy this just so it makes it easy for me. So let's see if I can just move this. I can. That's great. Hopefully I copied that. Copy. And then now I paste it here so that becomes my numerator. Great. But erase the du. Right, erase the du. Drag you over here. So that's the numerator. And did I even define what my d theta was at the end of the day? Oh, I forgot to put my d theta up here. Oops, my mistake. D theta, that's important. Yeah, and d theta over here. Okay, so what do we have? Okay, so next in the denominator we have u minus b squared minus r squared to the 1/2 power, right, over u to the 5/2. So u, oh my goodness. Okay, so u, if you remember carefully, right, did I not do all this right? No, I think it's fine. So u, remember, where was our definition? We had square root of u right down here, right down here. We had let square root of u is equal to square root of b squared plus r squared times secant of theta. So now we have to evaluate what is u minus b squared minus r squared in terms of this new substitution. So we'll get b squared plus r squared, right, secant squared of theta minus quantity b squared plus r squared. Right, so that's what our denominator is going to look like. So I have to remember that so I don't forget. So I'll have in the denominator down here, we'll have b squared plus r squared secant squared of theta minus b squared plus r squared to the, this is the 1/2 power, I think, right? I think that's the case. And then going back up, we have a u to the 5/2 power. So u to the 5/2, u is just b squared plus r squared secant squared of theta, right, times b squared plus r squared times secant squared of theta to the 5/2 power. Wow. Right. This is a mess, isn't it? And we still have a u to the 1/2, don't I, in the top? So on the top I have a u to the 1/2, and then we have u to the 1/2, remember, is just b squared plus r squared secant of theta, square root of that. Okay, so this u to the 1/2 up here is just the square root of b squared plus r squared to the secant of theta, right? So, goodness, lots and lots of substitutions that you have to be careful about. So, okay, after all this madness, let's just try and do some simplification here. In the numerator, and I forgot d theta. So in the numerator, what we can do here is, let's just write down here b to the 5. Maybe I should just drag this in a bit more. So I'll have b to the 5, 0, pi by 2, 2b to the 5, right? And then we have b squared plus r squared to the 1 power, secant squared of theta tangent of theta d theta in the numerator. And then in the denominator, a little bit more work, right? So we can factor b squared plus r squared. So we'll have in the first term, we have b squared plus r squared. That's factored out of secant squared of theta subtract 1, all to the 1/2. Then we have b squared plus r squared to the 5/2. I'm distributing this 5/2 up here to both terms. So then I'll distribute that. That becomes secant to the 5th theta. Okay. Wow. And I'm running out of breath, but it's okay. It's okay. We are closing in. We are getting closer. I'm telling you. So more simplification. 2b to the 5. 0 pi by 2, right? And then we have still the same b squared plus r squared secant squared of theta tangent of theta d theta. Then in the numerator, we're going to distribute this 1/2, so we'll have b squared plus r squared to the 1/2. But remember, we have a 1/2, and then we have a b squared plus r squared to the 5/2 here. So a 1/2 plus 5/2 is 6/2, that's 3, so we end up getting b squared plus r squared to the 3rd power in the denominator. So let me write that 3 a bit more clearly, because that's a little bit hard to see. 3. There we go. And then we have secant squared of theta, right? Secant squared of theta is just tangent squared of theta, right? So secant squared minus 1 is equal to tangent squared, right? And we have a 1/2 there. So that 1/2 on the tan squared theta becomes just tangent. So end up getting a tangent of theta in the denominator, which is great because it'll cancel with the 1 in the numerator, and we have a secant to the 5th power in the denominator, right? So that's it, right? That is all the simplification we can do. I can cancel one factor with one factor of b squared plus r squared to the 2nd power in the denominator. So we just have 1 over b squared plus r squared. Then we have a tangent theta canceling, and then we have a factor of secant squared canceling 2 factors of secant at the bottom, so we have 1 over secant cubed. And after all of that talking and all of that manipulation, we get something that looks like 2b to the 5th power over b squared plus r squared to the 2nd power, integrating now pi over 2, 1 over secant of cubed of theta. Oh my goodness, we have finally come to something that we can actually directly integrate. Because 1 over secant cubed, that is just another way of rewriting, right? So I'm just going to copy this to b to the 5, b squared plus r squared to the squared, and then 0 pi over 2. That's just cosine cubed of theta, d theta now. Yes, we can finally do this. So how do we integrate cosine cubed of theta? So after all of our hard work, how do we integrate this thing? Making sure we don't forget the prefactor outside. Right? What we can do, we can break that into a factor of cosine of theta and cosine squared of theta. And we can further break the cosine squared of theta into a 1 minus sine squared of theta from the identity, right? The identity that sine squared of theta plus cosine squared of theta is equal to 1. Okay, so using that identity, we have simplified that. Now we can perform yet another substitution. U is equal to sine of theta. Du is equal to cosine of theta d theta. That's great because the cosine of theta d theta is going to get replaced with a du. Now we just have to evaluate what our bounds are going to be now. We're going to have maybe I shouldn't call it u. We had u before, right? So let's just call it x, right? Let's just call it x because why not? X is equal to sine of theta. Dx is equal to cosine of theta d theta. So if theta is equal to 0, right, we'll have x is equal to 0, right, because sine of 0 is 0. Theta is equal to pi over 2. X is equal to 1, because sine of pi over 2 is 1. So now we get the integral from 0 to 1 of 1 minus, making sure I don't want to mess up here, so minus x squared dx. Is that correct? Looks like that's correct to me, so that ends up being x minus x cubed over 3. Evaluate that from x is equal to 0, x is equal to 1. So we get 1 minus 1/3, right? That's equal to 2/3. 2/3. Let's see, 2/3, right? And finally, right? This is the result of the integral, but now we just multiply it by the prefactor up there. So we have 2b to the 5 over r squared plus b squared, so that's big R squared, plus b squared squared times 2/3. And then finally, the final answer is 4 over 3b to the 5 over r squared plus b squared squared, boxed. So, whew, what an integral, right? Hope you've enjoyed this video. It was a very long integral. I did faster this time than how long it took me the first time doing this, but it still, all the substitutions you have to do, it's insane. So I really hope you enjoyed the video. Please subscribe if you like this, and stay tuned for more math problems. Thanks for watching.